Rotating wildly, flinging matter outwards, black holes are not the voracious monsters of science fiction, feasting on everything within reach.
The thing about a black hole is that they eat like they're toddlers. They're messy. So as stuff is falling in, a lot of it doesn't ever actually make it inside the black hole.
Physicists estimate up to 40% of the dust and gas in the accretion disk never enters the black hole.
It's only when you're inside the black hole that you're doomed. But just a little bit outside the black hole, if you're going around fast enough, you can exist that way for a long time.
Suspended between spin and gravity, the probe could be stuck here forever, doomed to gaze into the black hole's blank face, never knowing what lies beyond. But gradually, gravity is winning, dragging the probe ever closer to the edge of oblivion.
Black holes have something called the event horizon, and it's the point at which there is no escape from the gravitational pull of the black hole. Once you cross the event horizon, it's similar to going over the edge of a waterfall. There's no return.
If you look at this waterfall, you see it's sort of going flat, and then suddenly at the edge, water's falling steeply down. The edge of a black hole is sort of like that. At the event horizon, suddenly space begins to bend deeply in.
Gravity pulls the water across the edge and down the waterfall, in the same way that it pulls space and time over the event horizon and into a black hole.
Just like a fish exists in water, everything exists in space-time, and that includes light. So a little light ray falling over the event horizon of a black hole is never going to be able to come back out.
The only way to escape is to defy gravity. For water to travel back up the waterfall or light to escape from a black hole, it would have to travel fast enough to overcome the pull of gravity. And the stronger the gravity, the faster the object needs to travel. To escape the Earth's gravity, a rocket must travel at 7 miles per second. From our far more massive sun, the escape velocity soars to around 384 miles per second.
Black holes have gravitational fields that are so much stronger than that. In fact, rather than the speed of a rocket to escape, even if you go the speed of light, you'll never get off.
In the few remaining seconds before the probe tumbles into the abyss, the pull of gravity and its distortion of space-time goes off the scale. In the few remaining seconds before the probe tumbles into the abyss, the pull of gravity and its distortion of space-time goes off the scale.
Suppose I have a clock, and the probe has a clock, and I can observe the probe's clock and my clock. As the probe gets nearer and nearer the event horizon of the black hole, I will observe the probe's clock actually stop.
Right at the event horizon, time basically grinds to a complete halt. So if I were sitting on the event horizon of a black hole, or almost on it, and you looked at me, I would just seem frozen to you.
You never actually observe an object falling into the event horizon from the outside, because it will take longer than the age of the universe for us to watch the object disappear.
The black hole's extreme gravity distorts space, time, and light.
As you fell into a black hole, people would see you being redshifted. They would see light coming from you losing energy because it has to climb out of this incredible well of gravity to get out of the black hole.
We experience the same phenomenon with sound. When a fire truck speeds towards us, the sound waves compress. Racing away, they stretch out. Like sound, light travels in waves. But instead of changing pitch, light waves change color. Climbing out of the black hole's gravity, light waves stretch, lose energy, and turn red.
That's why black holes, in some sense, sound like the stuff of science fiction. But the real universe is stranger than science fiction. That's what's so wonderful. And what's even more wonderful is we don't know exactly what happens at the event horizon of a black hole.
Einstein's theory of general relativity predicts the probe will simply glide through the event horizon.
So this probe, if it's going past the event horizon, there's not going to be a signpost there that says, "Welcome to the event horizon." It won't notice anything different. You just cross this boundary, and then suddenly you're cut off from the universe, never to return again. That's pretty wild.
But according to a radical new theory, our probe's descent into the abyss won't be a gentle freefall. It will be a baptism by fire in the ultimate cosmic firewall.
So a computer firewall is simply supposed to be an impenetrable barrier, whereas the black hole firewall is literally a wall of fire.
And that means that it's not innocent near the event horizon. It's not just empty space with a few soft photons that you can barely notice. Rather, there's this hugely dense radiation bath of photons.
This new theory turns the event horizon into the most dangerous place in the universe, incinerating anything that touches it in an inferno of infinite energy.
There is no doubt that there is a place in space, the event horizon, the place from which nothing gets out. But the million-dollar question is what actually happens there if you jump in. Some people think that nothing special happens there, and other people think that you actually get burned up by this firewall. And what's so embarrassing about this is if you actually want to find out and decide to jump into a black hole, you will learn, but you can't tell anybody else.
The frustrating thing about black holes is because it has this event horizon and we know that light cannot be emitted past that threshold, even with all of our advanced telescopes, it's very difficult to detect.
To picture what happens at SAG A-STAR's distant event horizon, we'd need to build a telescope as big as the Earth. It sounds impossible, but it's already taking shape at Hawaii's Mauna Kea Observatory.
If you want to see the black hole at the center of the galaxy, you need a really, really big telescope. We can't build optical telescopes that big. And what we do is we use radio telescopes and we distribute those telescopes over thousands of miles apart from each other. So we're creating a telescope that's as big as the Earth itself. And over here is where it all comes down. And inside of this rack, all of our signals come in here at 8 gigabits per second. It's the equivalent of 4 digital movies per second. If we sent this back by your home internet connection, it would take years to transmit all of this data. So what we have to do is specially package this up and ship it to our central lab at MIT where we process this data.
This is essentially the holiest of holies. This is ground zero. This is where all the data come together.
The accumulated data could bring the event horizon into focus within 2 or 3 years.
So once the Event Horizon Telescope gets its final data sets, we hope to image something like this. This is what we wind up seeing, though, because the intervening gas to the center of our galaxy blurs the image. But if we take out the scattering, we wind up being able to recover the shadow feature. This is what we're after. This is the holy grail of the Event Horizon Telescope.
It's a black sphere, 17 million miles in diameter. Up close, this is what our probe should see in the final moments before it enters the abyss. If there is a firewall lurking behind this black veil, our journey ends here. If not, the probe simply glides across the point of no return to enter the most violent place in the universe, where new worlds begin and the past becomes the present. Our probe has survived a whirlwind of space and time. Now it's inside the supermassive black hole, plunging into a world of unimaginable violence that it can never leave.
Everything that falls into a black hole disappears. And if it never gets out, the question is, where does it go?
Gravity here is so intense, it accelerates space beyond the speed of light. At this speed, the 8 million-mile journey to the black hole's center will take less than 40 seconds, if the probe survives that long.
Now imagine that I'm falling into a black hole. The strength of gravity is going to be different if I'm going in feet first because of the extreme curvature of space-time there. And because of that, my feet will have a stronger pull and you'll get stretched into a form that's reminiscent of spaghetti. So we call it spaghettification.